Okay, so welcome to this next video in which we are discussing caged inositol trisphosphate. Okay, right. So we're just in the process of giving an example problem where we're going to use caged inositol trisphosphate, which is this problem of trying to work out why, when we knock out the selenoprotein K, the calcium flux upon activating the phosphoinositide pathway is reduced, basically. Okay, so basically the claim of the paper is that you have complexes in the ER membrane of this DHHC6 enzyme here, which is a member of the DHHC family of enzymes, which all palmitoylate proteins in the S fashion, okay, and selenoprotein K. So the claim is that these are going to form a complex. The SH3 domain of selenoprotein K will bind to the SH3 domain of DHHC6, and together that complex palmitoylates the IP3 receptor subunits, basically. Okay, and the claim is that without the selenoprotein K, the DHHC6 alone will not palmitoylate the IP3 receptor subunits, and without the palmitylation, the IP3 receptor stability in the ER membrane goes down, and the number that you end up having in the ER membrane is reduced, basically, and that is why the calcium flux upon activating the phosphoinositide pathway goes down, because there are less IP3 receptors in the ER membrane for the IP3 to act on. Okay, and we're going to see how caged inositol trisphosphate is going to help us understand that. Okay, right. We were discussing S-palmitylation, okay? So, I'm now about to show you what S-palmitylation actually involves. So basically, S-palmitylation involves sticking palmitic acid molecules onto cysteine residues within a protein. Okay, so let me draw a cysteine residue here. So here's the amino group, which will be involved in binding to the carboxylic acid group of the amino acid before it. Then we have the alpha carbon with a hydrogen coming off it, and then the carboxylic acid group again coming off the alpha carbon, and then bound to the amino group of the amino acid after it. Okay, and the R group of a cysteine residue consists of a methylene group and then a thiol group off that methylene group. Now, basically what we are going to do is transfer the palmitoyl group from the coenzyme A molecule onto the thiol group of the cysteine residue. So remember, at the present, we have, Ca, that should say Co-A, that should be an O there. Okay, so we have our Co-A molecule, which has a thiol group, which is linked to the palmitoyl group. So here's the carboxylic acid group, and here are our 14 methylene groups. So I'll draw one, bracket it, and put a 14 as a subscript. Okay, and then our methyl group on the end over here. Right, okay, so basically what we're going to do is we're going to break this bond between the carbon and the sulfur atom here. Okay, and remember, covalent bonds consist of two electrons, one from each of the two members of the bond. So in this single bond, there will be one electron from the sulfur atom and one from the carbon atom. Imagine returning the electron from the sulfur atom back to the sulfur atom, and the electron from the carbon atom back to the carbon atom. Okay, now what you'll also do is, on this thiol group off the cysteine residue, you will cut this bond here between the sulfur and the hydrogen, and you can imagine sending one of the electrons back to the sulfur and one back to the hydrogen. What you're now going to do is bind this hydrogen, which has a free electron, to this sulfur atom, which has a free electron, and hence regenerate the coenzyme A molecule. So here is coenzyme A, and it will now have its thiol group nicely regenerated. And what this will result in then is you then having this sulfur atom with a free electron and this carbon atom with a free electron, and what you'll do is bind that sulfur atom to this carbon atom, and hence you will have transferred the palmitoyl group onto the thiol group of the cysteine residue off the thiol group of the coenzyme A molecule, and again this palmitoyl group will be bound to the cysteine residue by a thioester link. Okay, now one more thing that I need to discuss with you is the structure of the IP3 receptors. Before we can actually discuss palmitylation of them, we do actually need to know something about their structure, because they are not just made up of a single protein, they're made up of several proteins, basically. So, let's now have a look at an in-detail drawing of the IP3 receptor. Okay, so the IP3 receptor is fundamentally a channel. It's going to allow calcium ions to move through it. At the moment it's closed and is not allowing calcium ions to move through it, but potentially it can open. So at the moment it's got a very narrow pore and calcium ions cannot move through that. Okay, but it is not one protein. Instead, it is 4 separate polypeptides which have all been stuck together to make a tetramer, basically. So it's made up of 4 separate subunits, basically. Okay, now if we pull out one of these subunits and have a look at its membrane-spanning topology, so now what I'm doing is I'm going to say, okay, I'm going to pull out one of these subunits that makes up the whole IP3 receptor, and I'm going to have a look at its membrane-spanning topology. Okay, and this side of the membrane is the cytoplasmic side, so this is the side facing the cytoplasm, and this side is the luminal side. Okay, so it faces the ER lumen. Okay, and now what I'm going to have a look at is the membrane-spanning topology of this protein. So basically the amino terminus starts off in the cytoplasm, so here's the amino terminus. Then we have a single membrane-spanning alpha helix, a second membrane-spanning alpha helix, a third, a fourth, a fifth, then it tries to span the membrane, fails, and then it finally manages a 6th time there to end with its carboxylic acid terminus, again in the cytoplasm. Okay, so this is the structure, the membrane-spanning topology of a single one of the subunits of the IP3 receptor. So this is the IP3 receptor over here. This, meanwhile, over here, is an IP3 receptor subunit, okay? Now, what would be very, very simple is if there was only one gene which coded for the IP3 receptor subunit, and that all you had to do was use this gene 4 times to make 4 proteins, stick those 4 identical proteins together to make an IP3 receptor. That would be extremely simple. However, it's not that simple. Basically, there are 3 genes which all code for IP3 receptor subunits, and all of these genes will have slightly different sequences of organic bases, and therefore they will code for proteins which have slightly different sequences of amino acids. But all 3 proteins are similar enough that they will all perform the same function. They'll all make up a quarter of an IP3 receptor, and they all have the same membrane-spanning topology, but they do differ slightly. So, these 3 separate genes are just called the IP3 receptor subunit gene 1, the IP3 receptor subunit gene 2, and the IP3 receptor subunit gene 3. Okay, and of course the actual proteins will then just be called the IP3 receptor, oops, what's happened there? The IP3 receptor subunit 1, the IP3 receptor subunit 2, the IP3 receptor subunit 3. Okay, so how do you now assemble these into tetramers, basically? Well, a simple way to do it would be to design your IP3 receptor so that the IP3 receptor subunits that you stick into each one of these 4 slots that you've got are exactly the same, okay? So for instance, you could take 4 IP3 receptor 1 subunits, stick them all together, and make what you might want to call an IP3 receptor 1. Okay, a type 1 IP3 receptor. Okay, you could do the same thing for number 2, and you could do the same thing for number 3. This type of tetramization is called homotetramerization, okay, and this would be called a homotetramer. Okay, so when you use the same subunits in all 4 sockets, it's then called a homotetramer. Now, you can make all 3 of the homotetramers, however, they're not the only type of IP3 receptors you can make. You can also make heterotetramers, and hetero means different. So in heterotetramers, you're going to have different subunit types in the same IP3 receptor tetramer. Okay, so you might put in an IP3 receptor type 1 subunit here, then you might put in an IP3 receptor type 2 subunit here, and that would be considered a heterotetramer. Now, so far, we have found IP3 receptor tetramers which have 2 different types of the receptor subunit in them. Okay, so we found, for instance, IP3 receptors which have IP3 receptor type 1 subunits and IP3 receptor type 2 subunits in. Okay, we haven't yet found IP3 receptors that have all 3 within them. Okay, but that doesn't mean they don't exist. Okay, so the scope for making a whole bunch of different IP3 receptors is very large, potentially. Okay, so IP3 receptors then, they are tetramers of these IP3 receptor subunits, of which there are 3, and you can make both homotetramers and heterotetramers. Now, another interesting fact about the IP3 receptors is that each one of these subunits is absolutely massive. They are around 2,750 amino acids long. Okay, so this polypeptide contains around 2,750 amino acids. That's big. It's not, as big as they can get. You can get proteins that are bigger than that, but that's a big protein, basically. Okay, and you are now going to assemble 4 of these things together to make an IP3 receptor, which means that these tetramers are absolutely massive, and they're actually visible under electron microscopy, basically. So these things are giants in the world of proteins. Right, okay, so basically the claim is that these complexes of DHHC6 with selenoprotein K that we've been talking about, okay, so I'll just draw one of these complexes here. So here is our DHHC6 enzyme. I'll just make sure that I extend the cell membrane a little bit. Okay, so here it is, and I want to just put the other protein in as well. So here's selenoprotein K. Okay, and this will have an SH3 domain which will be interacting with the SH3 domain of the selenoprotein K. Okay, so here is our DHHC6 enzyme here with an SH3 domain which is interacting with an SH3 domain on selenoprotein K. And basically the claim is that this complex of selenoprotein K here with DHHC6 is going to stick palmitoyl groups onto the subunits of the IP3 receptor. Okay, so they're going to get palmitoyl groups stuck on the side of them. And what's the significance of this? Well, basically, palmitoyl groups are hydrophobic. They have a great big long hydrophobic tail. The phospholipid bilayer has a lot of hydrophobic molecules in its core, basically. So these palmitoyl groups will implant into that hydrophobic core of the ER membrane. Okay, and this will stabilize the IP3 receptor subunit in the ER membrane. Okay, that's the idea. Okay, so if you now took out the selenoprotein K, which is what these experimenters did, they knocked it out, basically, okay, then these complexes will no longer be present because the selenoprotein K won't be present. Now, when DHHC6 doesn't have selenoprotein K, it will not palmitoylate the IP3 receptor subunits. Okay, so the IP3 receptor subunits will not get these palmitoyl groups added onto their cysteine residues anymore, which means that the IP3 receptors are going to become less stable in the ER membrane, and the speed with which they're going to be removed from the ER membrane and degraded increases, basically. So you don't change the amount of IP3 receptor subunits that you're constantly producing, but the rate at which they're removed from the ER membrane and destroyed will be increased. So you can understand, therefore, that the number that you actually have in the ER membrane at any one time will decrease. So when you when you activate the phosphoinositide pathway in these selenoprotein K deficient cells, what will happen is you'll produce the same amount of IP3 as ever, and this IP3 will then activate the IP3 receptors, okay? It'll prime them for being opened, and as far as we're concerned, we'll simplify it to just saying that the IP3 is going to lead to the release of calcium from the IP3 receptors. Okay, but because you have fewer IP3 receptors, the amount of calcium that you're going to get released from the ER is going to be reduced, because the amount of IP3 receptors you've activated to open will be reduced. Okay, so the calcium flux would therefore be reduced. That's their explanation for the experimental result, which is that if you knock out selenoprotein K, the calcium flux goes down. Now, we are now going to look at an experiment which they did in this paper using caged IP3, which shows us that knocking out selenoprotein K does not affect how much IP3 you produce. So, if you activate the phosphoinositide pathway, let's say you expose the cell to a certain amount of histamine, maybe, which activates H1 receptors, which then activates the GQ heterotrimeric G protein, which then activates phospholipase C beta, which cuts PIP2 into IP3 and DAG. And you expose the cell to a set amount of histamine, let's say. So the amount of activation of the phosphoinositide pathway doesn't change, basically. What we want to show is that knocking out selenoprotein K does not change the amount of IP3 that is produced for a certain activation of the phosphoinositide pathway. Because when we have an experimental result like so, that selenoprotein K knocking out that causes a reduction in calcium flux, there is absolutely loads of stages of this phosphoinositide pathway that could be affecting. It could be affecting the generation of IP3. So what we're going to do is show that it's not the generation of IP3. And the way that we're going to do this is we're going to use caged IP3. So let's now talk about caged IP3. Now, before we go on to caged IP3, I want to talk about the structure of IP3 firstly, so that we can then understand the structure of caged IP3. And before I can talk about the structure of IP3, I need to talk about the structure of inositol. So, IP3 is short for inositol 1,4,5 trisphosphate. Okay? So the I is for inositol, and then the P3 is for phosphate, and then you've got 3 of them, so you put a 3 underneath. So this is inositol 1,4,5 trisphosphate. So before we discuss inositol 1,4,5 trisphosphate, let's discuss this molecule inositol here. Okay, so there is another name for inositol. The chemist's name for inositol is cyclohexane 1,2,3,4,5,6 hexol. Okay, so the chemist's name for this is cyclohexane, okay, which means a 6-membered carbon ring where all of the bonds between the carbons are single bonds, and then it's 1, 2, 3, 4, 5, 6 hexol. So every single one of the carbons in the ring has an alcohol group coming off it. Okay, so we'll start by drawing a skeletal structure of cyclohexane. So, cyclohexane here is a 6-membered carbon ring, and remember in skeletal structures we don't show carbons, so we just draw it as a hexagon. Okay, so each of these corners implicitly denotes a carbon. Okay, and all of them are singly bonded together. Now in cyclohexane what you then have is two hydrogens off each of these carbons. So each of these carbons has 2 bonds at the moment. So it also has 2 bonds free, and what you would have is hydrogens bound to each of these. You'd have 2 hydrogens bound to each of these carbons. Okay, right. And that would take you up to 4 bonds. So that's the structure of cyclohexane. To turn this into cyclohexane 1,2,3,4,5,6 hexol, what you would then do is remove a hydrogen from every single one of these carbons. So you'd go around ripping the hydrogens off, and you'd replace them with alcohol groups. So we'll put an alcohol group on here, we'll put an alcohol group on here, we'll put an alcohol group on here, and I should have just said at the point when I was discussing cyclohexane, in skeletal structures you don't show hydrogens coming off carbons, which is why I didn't show 2 hydrogens coming off these carbons. Okay, anyway, we've removed one of the hydrogens that comes off each of the carbons and replaced it with an alcohol group. So now each carbon in the ring now has 2 groups coming off it. It has a hydrogen atom coming off it, and it has an alcohol group coming off it. And this is the structure of inositol, or cyclohexane 1,2,3,4,5,6 hexol. Now, this is beautiful and simple. However, it's far, far more complicated than that, because there's a monster here, basically, which is optical isomerism. Every single one of these carbons is a chiral center, basically. Okay? Appreciate that, because if you think about it, let me draw this again. If you think about having your cyclohexane here, let's imagine that this six-membered carbon ring is sitting within the plane. Okay? And now each one of these carbons has an alcohol group coming off it, and also a hydrogen coming off it. Now there are two groups coming off each one of the carbons, and one of the groups has to come out of the page towards us, so it will be coming off at an angle like this, and one of them has to go into the page away from us, basically. Okay, and these bonds are not free to move around, basically. You know, the molecule isn't constantly swapping which one is coming out of the page towards us and which one's going into the page away from us. They're rigid. So, basically, how do you decide whether the alcohol groups are coming out of the page towards us and the hydrogens going into the page away from us, or whether the hydrogens are coming out of the page towards us and the alcohol groups are going into the page away from us? Basically, it's going to lead to a whole bunch of optical isomers of this inositol molecule. And you might think, well, okay, if you were going about this logically, what you'd say then is, okay, each one of these has two conformations it can be in. Either the alcohol group can be coming out of the page towards us and the hydrogen is going into the page away from us, or the alcohol group is going into the page away from us and the hydrogen is coming out of the page towards us. So this has two conformations it can be in, this one has two, this one has two, this one has two, this one has two, this one has two. So surely I just take 2, multiply it by this 2, multiply it by this 2, 2, 2, 2, multiply all the 2's together, get 2 to the power of 6, and that will be the number of optical isomers that I have. But if you do that, what you will hopefully realise is that loads of those optical isomers will be equivalent, basically. You'll be able to turn one of them into another one just by rotating the molecule. So in fact, there are only 9 optical isomers of inositol. I say only 9. That's quite a lot. But we'll go through these nice and gently because it's a specific inositol molecule that is mainly expressed within cells. The others are quite negligible within cells, so we want to understand which optical isomer it is within cells, and this will also help us to understand why this molecule is called inositol 1,4,5 trisphosphate rather than inositol 1,3,4 trisphosphate. Okay, right, so let's start off with the first optical isomer. So an obvious first optical isomer to think about is where all of the alcohol groups are on the same side, basically, of this ring. So let's draw it as all of the alcohol groups going into the page away from us. And the reason I'm doing this rather than out of the page towards us is just because I prefer drawing the symbol for bonds going into the page away from us than bonds coming out of the page towards us. So to avoid having to draw 6 bonds coming out of the page towards us, I'm drawing them going into the page away from us. So basically all of the alcohol groups are on the same side of the molecule, the same side of the ring. They're all going into the page away from us, and that means that the hydrogens coming off these carbons are all coming out of the page towards us. So this is a beautifully rotationally symmetric molecule. It's got rotational symmetry 6, basically. Now, this is exactly the same molecule as if I had drawn all of the alcohol groups coming out of the page towards us and all of the hydrogens going into the page away from us. I hope you can understand that, because if I just took this molecule and rotated it around, just grabbed the whole thing, I'm not changing any chemical bonds now, and just rotated it around, or even better, if I just rotated myself around and viewed from another side, if I viewed from underneath the page rather than from above the page as I am doing, I would see these alcohol groups as all coming out of the page towards me. So this is the same molecule as if I had drawn them all coming out of the page towards me. What's important is that all the alcohol groups are on the same side of the molecule. Now this optical isomer of inositol is what's called cis inositol. So cis means on the same side, so that makes sense, because all the alcohol groups are on the same side. So there's our first optical isomer of inositol. Okay, so let's work through this in logical order. What's the obvious thing to now change? Well, the obvious thing to now do is just move one of these alcohol groups so that it's on the opposite side to the others. Okay, so what I'll do is I'll take one of these and move it so that it's on the opposite side to all the others. Okay, so here is our six-membered ring again, and I'll just happen to choose this one, although it doesn't matter. Okay, so I'll choose this one, and I'll make this one coming out of the page towards us, whilst all of the others stay on the other side, so they're going into the page away from us. So now there's just one that is the odd one out, basically, and this ruins the rotational symmetry of the molecule completely. Okay, right, this isomer of inositol is called epi-inositol. Okay, so this is epi-inositol. So when you have one alcohol group coming out of one alcohol group on one side of the ring and the other 5 on the other side of the ring, that's called epi-inositol. And I hope you understand that this is exactly the same as if I had chosen this one off here to be the alcohol group that comes out of the page towards us. Because if I just rotate this around by, 60 degrees, I will have got, I can turn it into the drawing that I would have drawn if I picked this one to come out of the page. So basically, this is the same as a whole bunch of different molecules. Just by rotating it around, you can turn it into a whole bunch of different molecules. What's important is that one of them is on one side and the other 5 are on the other side. Okay, so anything where you have 5 alcohol groups on one side and 1 on the other will always be the same as this. Just by changing the way you look at it, you can change it into that and superimpose it on this drawing. Okay, so that's the second optical isomer of inositol. Now that's the only optical isomer which you can have where there is 1 on one side and 5 on the other. So this is the one optical isomer you can have where there's 6 on one side and 0 on the other. So this is 6 versus 0. And this is the only optical isomer you can have where there's 5 on one side and 1 on the other. So we now go up a stage. We go to 4 on one side and 2 on the other. Okay, and this gets more interesting. There's more than one optical isomer where there are 4 on one side and 2 on the other. So, let's go. So, again, let's draw our cyclohexane out here. So here is our ring of 6 carbon atoms. And now we need 2 alcohol groups to be on one side, which we'll have coming towards us, simply because I prefer drawing going away than coming towards us, because that symbol's more difficult to draw than dotted lines. Okay, so firstly we could just have the 2 alcohol groups that are coming out towards us next to each other as one option. So let's start off with them as being next to each other. Okay, so here are 2 alcohol groups next to each other, and they're on one side, and the other 4 are on the other side. Okay, so these are all going away from us, and therefore the hydrogens of all of these carbons are coming towards us. Right, so this is an optical isomer of inositol, and this form of inositol is known as allo-inositol. Okay, right, and again, hopefully you can see that if I rotated this around by 60 degrees, I would have an alcohol group coming out here, and an alcohol group coming out here, and an alcohol group here that goes into the page. So this is why, basically, that argument of 2 to the power of 6 didn't work, because it didn't take account of the fact that I can rotate this in loads of different ways and get loads of the things that I would have been counting as separate optical isomers if I'd been using this logic, just by rotating a single optical isomer. Okay, so that's where you would have to be careful with this argument, basically. You'd have to be very clever. You'd have to know a lot of group theory to go from that argument. Okay, and in this case, it's best just to think logically rather than to use advanced mathematics. Okay, right. Let's go to the next one. Okay, so what would we think intuitively we should do next? So my claim is that this is not the only optical isomer where you have 4 on one side and 2 on the other, because this had the 2 that were on the opposite side to the other 4 next to each other. Why don't we, have them not next to each other? Okay, so let's. Oh, I need another piece of paper. So we've now got 3 optical isomers, but let's progress forward. So. Again, let me draw my cyclohexane ring here. Okay, and what you would have is now what we want is the 2 alcohol groups that are on the opposite side to the other 4, which I'm drawing as coming out of the page. Let's have them with an alcohol group that's going into the page away from us, between them basically. So let's have a carbon in between them here. Okay, now the other 4 will all be going into the page away from us. Now this is a separate optical isomer to the aloe inositol that we've just seen. Okay, no matter how you change the way you're looking at this molecule, no matter how you move around to look at it from different angles, you cannot make this look like aloe inositol. You just can't. You can't superimpose the two. So they are fundamentally different molecules, and you can't change them into one another without performing a chemical reaction. Okay, now this form of inositol is very, very important. This is the one that is present within cells. This is called myo-inositol. Okay, so this is highly expressed within cells, and this is the one that we will use when drawing the structure of inositol 1,4,5 trisphosphate. Right, so we'll come back to myo-inositol, but for now, that's a structure of it. Now, continuing on with the isomers of inositol, because we have to finish it now. And now that we've started it, we have to finish it. Okay, so there is another one where you have 2 on one side and 4 on the other. Because what if we put them diagonally opposite? Let's move this one to here now. Okay, so let's go further. So, again, here is our cyclohexane ring. Okay, and now the 2 alcohol groups that are coming out of the page towards us, those will be diagonally opposite one another. So one will have there, and one will have down here now. And like so. And then the alcohol groups that come off all the other carbons, those will be going into the page away from us. So one here, and then one here, and then the final one here. So this is still an optical isomer of inositol where you have 4 alcohol groups on one side of the ring and the other 2 on the opposite side. But this is a different optical isomer from aloe inositol and myo-inositol, and this is what's known as muco-inositol. Okay, so muco-inositol next. Right. Now, muco-inositol is the final optical isomer where you have 2 on one side and 4 on the other. The next 4 optical isomers, which takes us up to 9, are 3 and 3 basically. 3 on one side and 3 on the other, so they're equal. Okay, so let's start this off. So, firstly, the obvious example. So just like aloe inositol was the obvious example when you had 2 on one side and 4 on the other, the obvious example if we're making 3 on one side and 3 on the other is just to group them together. So let's have the 3 alcohol groups that are coming out of the page towards us all over here next to one another, like so. Okay, and then we'll have all of the alcohol groups that are on the opposite side, i.e. which are going into the page away from us, on this opposite side over here. Okay, so 1, 2, and then 3 here. Okay, and this form of inositol is what's known as neo-inositol. Okay, so when you have all of them clustered together, that's called neo-inositol. Right, okay, now again what we have to explore is the other optical isomers which have 3 and 3 on one side. So let's start by putting a gap in between these 3 basically. So initially we'll just make it a single gap basically. So we're going to put one alcohol group in between these two alcohol groups which are coming out of the page towards us. So we're going to put here basically an alcohol group that's going into the page away from us, and we'll put here an alcohol group that's coming out of the page towards us. So let's start off again by drawing our cyclohexane ring here. Okay, so this is cyclohexane. Now we'll keep these two alcohol groups here constant. Okay, so we'll fix this one, and we'll fix this one here as well, like so. But now we're going to move this one round to here. Okay, like so. And we'll have an alcohol group here which is going into the page away from us, and we'll have an alcohol group here that's also going into the page away from us, and we'll also have an alcohol group here that's going into the page away from us. Okay, now we're going to have to call it there for this video, but we'll continue this discussion in the next video.